There's a number at the center of all of modern cosmology. It tells you how fast the universe is expanding, how quickly galaxies are flying away from each other, how old the universe is, what its ultimate fate is going to be. It's called the Hubble constant, and we've been trying to measure it with precision for almost 100 years. And here's where things get uncomfortable. We've now measured it in two completely independent ways, with two completely different physical methods, with two teams of some of the most careful observational astronomers alive. And the numbers don't agree, not by a little, not within the measurement errors. The discrepancy is statistically significant, somewhere between 4 and 6 sigma, depending on which measurements you stack. And it has been growing steadily more severe with every refinement we make. The better we measure, the worse the disagreement gets. And right now, the field is split between two explanations, each of which, if true, would require rewriting something fundamental about our picture of the universe. Let me take you through how we got here, because this didn't happen overnight, and the path matters. Part 1. How you measure the speed of everything first. Why is measuring the expansion rate hard at all? The basic idea sounds almost embarrassingly simple. Edwin Hubble showed in 1929 that galaxies are receding from us, and the farther away they are, the faster they're moving. Velocity equals the Hubble constant times distance, h0 times d. So measure the velocity, easy, you can get that from the redshift of light, and measure the distance and divide. Done. The problem is that last part, measuring astronomical distances, because you can't put a ruler between here and a galaxy 100 million light years away. You have to build what astronomers call the cosmic distance ladder, a series of overlapping techniques, each calibrated against the last, each carrying forward the errors of everything below it. The bottom rung of the ladder is parallax. You watch a nearby star from opposite sides of Earth's orbit, 6 months apart, and measure how it appears to shift against the background of more distant stars. Basic trigonometry. This works out to a few thousand light years. Solid, reliable geometry. Then you use those parallax-calibrated stars to calibrate Cepheid variables, a specific type of pulsating star that has a precise relationship between how fast it pulsates and how intrinsically luminous it is. Measure the pulsation rate. You know the intrinsic luminosity. You compare to the apparent brightness, and you get the distance. Henrietta Swan Leavitt discovered this relationship in 1908, and it is genuinely one of the most important discoveries in the history of astronomy. It extended our reach to tens of millions of light years. Then you use Cepheids in nearby galaxies to calibrate type Ia supernovae, a specific kind of stellar explosion that, thanks to the physics of how it ignites, produces a remarkably consistent peak luminosity. Standard candles. You see a type Ia supernova in a distant galaxy, you measure its brightness, you know how bright it actually was, and you get the distance. This extends the ladder to billions of light years. Cosmological scales. That's the first method for measuring h0, sometimes called the distance ladder method or the late universe measurement. The most prominent ongoing effort is the SH0S team, led by Adam Rees at Johns Hopkins, who, by the way, shared the Nobel Prize in 2011 for discovering that the universe's expansion is accelerating. Their current best value for the Hubble constant is around 73 kilometers per second per megaparsec. What that means, for every megaparsec of distance, about 3.26 million light years, a galaxy is receding from us 73 kilometers faster. Write that down. Part 2, reading the baby picture of the universe. Now the second method, and this one is entirely different in kind, not just in technique, but in philosophy. The cosmic microwave background radiation, the CMB, is the oldest light we can see. It comes from roughly 380,000 years after the Big Bang, when the universe cooled enough for protons and electrons to combine into neutral hydrogen, and the universe suddenly became transparent. Before that moment, light was trapped. The universe was a dense, opaque plasma. After that moment, light traveled freely in all directions. We see it today as a faint glow coming uniformly from every direction in the sky, shifted to microwave frequencies by 13.8 billion years of cosmic expansion. It is not perfectly uniform. There are tiny temperature fluctuations, hot and cold patches at the level of 1 part in 100,000. And those fluctuations are not random. They have a characteristic scale, a preferred angular size, that comes from acoustic oscillations in the early universe plasma. Sound waves essentially frozen into the distribution of matter at the moment the universe became transparent. Here's the crucial point. The angular scale of those fluctuations tells you about the geometry of the universe. And to translate angular scale in the sky into a physical measurement, you need to run the entire expansion history of the universe forward from the Big Bang, using the standard cosmological model, which includes the amount of dark matter, the amount of dark energy, the density of normal matter, and yes, the Hubble constant. The whole thing is tightly coupled. You fit the model to the CMB data, and out comes H0 as a derived quantity. The Planck satellite, the European Space Agency mission that spent 4 years mapping the CMB from 2009 to 2013 with data analysis continuing for years afterward, gives a Hubble constant of around 67 kilometers per second per megaparsec. That's not 73. The difference is 6 kilometers per second per megaparsec. That sounds small. In cosmological terms, it is not small. It is the difference between two incompatible pictures of the universe, and the statistical significance of the discrepancy is currently sitting at around 5 sigma, which means if the measurements were consistent, you'd expect a deviation this large to arise by chance, roughly once in 3.5 million trials. This is the Hubble tension, and it has been sitting at the center of cosmology like a splinter for the better part of a decade. Part 3. The suspects. When two careful measurements disagree by 5 sigma, there are exactly 3 possibilities. One of the measurements is systematically wrong. The tension is real and both measurements are correct, which means the standard cosmological model is incomplete. Or there's something subtler going on, a methodological assumption shared by both approaches that's quietly wrong. Let's take them in order. Systematic errors in the distance ladder. This is where a lot of scrutiny has been directed, and fairly so. The distance ladder carries error at every rung. Maybe the Cepheid calibration is slightly off. Maybe the period luminosity relationship has a metallicity dependence, meaning it works slightly differently in galaxies with different chemical compositions. Maybe type Ia supernovae are not quite as standard as we thought. Maybe there's a population of slightly different explosions masquerading as the standard kind. The Hubble Space Telescope KEYS program, an independent effort led by Wendy Friedman using a different calibrator called the tip of the red giant branch, initially seemed to get a lower value, closer to 69 or 70, which looked like it might close the gap. But subsequent analysis found potential systematic issues with that calibration too, and the tension has persisted. The JWST, the James Webb Space Telescope, has now looked at Cepheids in the same galaxies that the SES team used, with unprecedented resolution, checking whether the Hubble Space Telescope's measurements were contaminated by crowded stellar fields. The answer so far? No. The Cepheid measurements hold up. The JWST confirmed SH0ES's calibration at around 73. The tension didn't go away. Systematic errors in the CMB measurement. This is harder to argue because the Planck results have been reproduced by independent ground-based experiments. The Atacama Cosmology Telescope, the South Pole Telescope, which all get consistent values in the 67-68 range. The CMB measurement is robust, unless, of course, there's a systematic assumption baked into all CMB analyses that's just wrong. And the obvious candidate there is the cosmological model itself, which brings us to new physics. Part 4. What breaks the standard cosmological model, LCDM for lambda cold dark matter, has been remarkably successful. It predicted the structure of the CMB before it was measured with precision. It explains the distribution of galaxies. It accounts for the formation of the first stars. It works. Except for this one number, there are broadly two directions in which new physics could resolve the tension, and they pull in different conceptually opposite ways. The first direction is called early dark energy. The idea, in the very early universe, before the epoch of the CMB, in the first few 100,000 years, there might have been a brief period of enhanced dark energy, a scalar field that was briefly dominant, then faded away. This would have had the effect of accelerating the expansion slightly in the early universe, which would shrink the sound horizon, the physical scale that the CMB fluctuations are set by. A smaller sound horizon means the CMB predicts a higher expansion rate, closer to 73. Several groups have worked out detailed models. They more or less work in the sense that they can move the CMB-derived H0 toward higher values. The problem, and this is a serious problem, is that fitting early dark energy to the CMB doesn't just change H0, it changes other parameters too. And some of those other parameters, when you propagate them forward to predict things like the clustering of galaxies in the present-day universe, get worse, not better. You fix the Hubble tension and you open something called the Cepheid tension, a disagreement between the predicted and observed amount of matter clustering. The early dark energy solution is a balloon. You push on one side and it bulges on the other. The second direction is late dark energy, or more generally, modifications to gravity or dark energy in the late universe. Maybe dark energy isn't actually constant, as LCDM assumes. Maybe it evolves with time. Maybe it was slightly stronger in the recent past. This would change the expansion history in a way that could be consistent with both the CMB and the distance ladder. Some recent hints from the Dark Energy Spectroscopic Instrument, DESI, which has been measuring the clustering of hundreds of millions of galaxies to reconstruct the expansion history, suggests that dark energy might not be a pure cosmological constant, might be slightly evolving. The statistical significance is modest, somewhere around 2 to 3 sigma, and could still be a systematic effect. But if it holds up with more data, it changes everything. And there's a third, less discussed option that some theorists are quietly pursuing. Maybe the problem is in neither the early nor the late universe, but in the local universe. Maybe the Milky Way and its neighbors sit in a slight underdensity, a void that would make locally measured distances slightly different from the cosmic average. This could shift the distance ladder H0 down slightly, towards 71 or 72, without new fundamental physics. It doesn't fully close the gap, but it takes it below 5 sigma. Part 5. What's actually at stake? Here is what I want you to sit with for a moment. LCDM, the cosmological standard model, is one of the most successful scientific theories ever constructed. It describes the evolution of the universe over 13.8 billion years with a handful of parameters, and it fits an enormous range of observations. It is not a rough sketch. It is a precisely calibrated, mathematically rigorous, observationally verified description of reality at the largest scales, and it disagrees with itself by 5 sigma. That deserves the weight it has, because 5 sigma might be a fluke. 5 sigma is the threshold that particle physicists use to claim a discovery. When physicists announced the Higgs boson in 2012, they had 5 sigma. The Hubble tension has 5 sigma. The difference is that a 5 sigma signal tells you something is there. A 5 sigma discrepancy tells you something is wrong. And what it might be wrong with is the framework that has organized cosmology for 40 years. The uncomfortable truth is that there is no leading solution to the Hubble tension right now. Not one that fits all the data without creating problems elsewhere. Every proposed modification of LCDM has a cost. Every appeal to systematic error has been challenged. Every instrument crosscheck has come back consistent. The tension refuses to resolve. Part 6. What comes next? Several things are about to change the picture significantly. DESI's full 5-year survey will be complete in a few years, and it will have mapped the expansion history of the universe in enough detail to either confirm or rule out evolving dark energy at high significance. If dark energy is changing, DESI will see it. The Vera Rubin Observatory, just beginning its legacy survey of space and time, will find hundreds of Type Ia supernovae per year. Orders of magnitude more than any previous survey. Statistical errors on the distance ladder will shrink dramatically. If the tension is due to some undetected systematic in supernova photometry, Rubin will find it. If it's not, that becomes correspondingly more clear. The Euclid mission, ESA's dark energy satellite launched in 2023, is measuring weak gravitational lensing and galaxy clustering across a third of the sky. It will constrain HR0 from a third independent direction using neither the distance ladder nor the CMB. This is critical. If the CMB and Euclid agree and the distance ladder doesn't, the problem is in the distance ladder. If all three disagree, the problem is in the model. And for gravitational waves, LIGO and Virgo, there is a completely independent method of measuring H0 that doesn't rely on the distance ladder at all. When two neutron stars merge, the gravitational wave signal tells you the absolute distance to the source. The wave's amplitude encodes it directly. You also measure the recession velocity from the electromagnetic counterpart. Divide distance into velocity, and you get H0, independent of Cepheids, independent of supernovae, independent of the CMB. The first such measurement from the 2017 neutron star merger GW170817 was consistent with about 70, roughly between the two camps, but with error bars large enough to be consistent with either. More mergers will sharpen this. Within a decade, the gravitational wave H0 might be the tiebreaker. What you're watching right now is a field wrestling with the possibility that it has been making a wrong assumption about dark energy, about the early universe, about the structure of the local universe, and genuinely not knowing which assumption it is. The data is good. The methods are careful. The disagreement is real. We measured the expansion rate of the universe twice with independent methods, and we got two different answers. And that gap, 6 kilometers per second per megaparsec, sitting there stubbornly between 67 and 73, is one of the most important unsolved problems in all of physics. The universe is telling us something. We just don't speak the language yet. Drop a comment. Do you think the tension points to new physics? Or is there still a systematic error hiding somewhere?